Okay, so we will actually go into these arenes. Okay, so arenes we have benzene and methyl benzene. So if you look at these arenes, okay, these are the one that the objectives, okay, that you need to cover in your syllabus. Okay, and we will actually cover everything in this lecture. Now, if you look at benzene, yeah, so we have already learned benzene, okay, it's going to be hexagonal shape, okay, made of 6 carbon atoms, okay, and then we say organic hydrocarbons, okay, with benzene ring, they are called arenes, yeah, aryl compounds, aromatic compounds, okay, and you should know that the simplest structure is C6H6, okay, benzene, okay, the structure, this particular structure was proposed by Frederick August 1865, and benzene is a planar and perfectly symmetrical molecule. Okay, but we also have learned that, okay, there are evidences that we can use, yeah, to reject the old benzene structure with the 3 double bonds over there. Yeah, so one of the evidence is going to be according to Kekulé structure. Yeah, there are 3 shorter carbon-carbon double bond. You can see from the table over here, carbon-carbon double bond, yeah, is shorter. Okay, carbon-carbon double bond here is shorter, and carbon single bond carbon is going to be longer. So if you put them together, yeah, so it will not give you a perfectly symmetrical hexagonal structure. Yeah, so you are going to get a distorted hexagonal shape. Therefore, okay, that benzene structure with the 3 double bonds are rejected. Yeah, apart from this bond length, okay, there are other evidences that we can use to reject the old benzene structure, which is going to be, okay, generally when you have double bonds, we are expecting, yeah, the structure to undergo electrophilic addition reaction. Okay, but benzene do not undergo electrophilic addition easily. It requires harsher condition, yeah, if you want to go through addition reaction. This is the reason is because the benzene ring, they stabilize the structure. The benzene ring, they want the electrons to just move within the ring. They don't want to let go of the electron easily. This one is known as, this is the first time I'm using this term. Okay, please take note. This is known as aromatic stabilization. Okay, the stabilization that is going to be used, okay, by the benzene ring itself. And we also know that each carbon in the hexagonal ring, because they form 3 sigma bonds over there, therefore you need to have 3 orbitals. So therefore, it is going to be sp2 hybridization. Yeah, we have already went through this. And each carbon atoms, they form, yeah, 3 sigma bonds. Okay, and each carbon atoms, they contribute 1 electron. Yeah, if they ask you from which orbital, then they contribute from 2p orbital. Yeah, or to be exact, 2pz. Yeah, so refer to the hybridization lecture or hybridization video that I put in the channel. Yeah, so here, okay, they contribute 1 electron to the pi bond. That makes it to have 6 electron in the benzene ring. Yeah, 6 electrons in the benzene ring. You can see the structure. Yeah, the delocalized electron, the benzene ring is going to cover at the top and at the bottom, so they move around. And the difference, yeah, between the delocalized electron in benzene, if you compare with alkene, is going to be the electrons are not attached to that carbon anymore. They keep on moving. Okay, but when it comes to alkene, yeah, that electron, they are attached, yeah, to a certain particular carbon atom, even though they can move. Yeah, that's the difference. Okay, that's a difference. Yeah, naming, we have already went through the naming part. Yeah, so sometimes we use chlorobenzene, nitrobenzene, like similar. Yeah, but sometimes, okay, we have to use the phenyl term. Yeah, so phenylamine, okay, or phenol. Yeah, so please take note. Yeah, when do we use the benzene term? When do we use the phenyl or phenol, phenylamine? Yeah, so these two will use the benzene. This will actually use the phenol. Yeah, so phenol and alcohol, they become phenol. Yeah, so this one is going to be the naming. Yeah, we can actually go in detail later when we use the compound. You will understand better. But when you look at the reactions of arenes, yeah, the reactions of arenes, okay, basically it relates to the benzene ring. Okay, the electrons in the benzene ring. So if you have, let's say, for example, the delocalized pi bonding electron, they remain intact for most reactions. And just now also I have introduced this term, aromatic stabilization. So because they like to remain intact, they don't want to let go of the 6 electron, they like to stay together. Yeah, so they actually stabilize the benzene structure. We call it as aromatic stabilization. Therefore, the initial attack, yeah, is done. Generally, you see, the initial attack must be done by the electrophile. Why? Because benzene, yeah, the benzene ring contains a lot of electrons. So high density of electrons around the benzene ring. So of course, it's going to attract electrophiles. Yeah. So if you look over here, okay, we actually went through the reaction. Yeah, electrophilic substitution reaction. So why it is substitution reaction? You can see from the main equation itself. Yeah. So earlier we have the hydrogen. Now the hydrogen is going to be substituted by Br. Okay, so when you react with Br2, okay, with the presence of catalyst, okay, the H is going to be substituted by Br. Okay, so that's why it's going to be called as electrophilic substitution. Now, that is one thing that I want you to remember. Yeah, this one, remember, I told you I will update the notes, okay, based on the new syllabus. This one, okay, I put it as here, okay, using FeBr3 and so on. I'll still use that because that appears in your textbook. Okay, but okay, this is very, very important. Please take note. Okay, I have actually taken from the syllabus over here. Substitution reactions with Cl2 and Br2, okay, they happen in the presence of, yeah, they happen in the presence of catalyst. Okay, okay, hold on, I think it's actually lagging. Yeah, hold on. Okay, can you still hear me, Ellen?
Yes, sir.
Yeah, I'll continue. Yeah, please take note. This is very, very important. Yeah, substitution reactions of Cl2 and Br2. Yeah, happens with the presence of catalyst. They have changed the catalyst or removed the FeBr3 and FeCl3. They have replaced it in the new syllabus as AlCl3 and AlBr3. Very, very, very important. Yeah. Therefore, okay, from now on, you need to make some changes over here. Okay, they react with bromine. Yeah, with what catalyst? Yeah, you change this one into AlBr3. Yeah, this one you can remove already. Okay, electrophile, okay, of bromine is going to be created when what? Okay, AlBr3 polarizes a bromine molecule. Okay, the bromine molecule forms a dative bond by donating a lone pair of electrons to an empty d orbital of, okay, of iron. You change it to aluminium. Yeah, the Br cation and the electron rich benzene attracted to each other. So here, okay, so what you need to change, yeah, basically we are going to use AlCl3 catalyst. Yeah, and then, okay, the mechanism you see, okay, Br2, okay, they will react. This one just change it into AlBr3. Okay, and this one change it to Al. Okay, just change it to Al. Yeah, so the this one is Al. Okay, this one is Al. Okay, just, okay, change it. Okay, but if you look at this mechanism, you see the first thing is they are trying to react with the catalyst and try to get the electrophile. And what the electrophile will do, the electrophile, okay, will be attacking the benzene ring. Okay, but you see the movement of electron is shown by the curly arrow, yeah, from the electron. Okay, so you need to show from the electron itself. Yeah, so you need to show from the electron itself. Okay, so the curly arrow is moving from the benzene ring to the Br plus. Okay, and after that, okay, you have these positive charges, and 2 electron went out, okay, to form the bond with the Br. Okay, therefore they need another 2 more electrons. So the 2 electron comes from here. Okay, they start to go in the benzene ring, and therefore, okay, they will actually, the H plus will go out. Okay, that H plus will join, yeah, together with this, okay, and they will create this HBr and AlBr3, yeah. But if you don't understand, it's okay, yeah, there is going to be, I'll show you here, yeah. So here, okay, that is going to be the previous notes is talking about reaction with Br2. So they do react with chlorine also, yes, yeah, with what catalyst just now, AlBr3. So now you change this into AlCl3. I think last time they still put the AlCl3. Now you just need to remove the Fe only. Yeah. So this AlCl3 and Br3, they are known as catalysts and halogen carriers. Yeah. So to write the mechanism of the reaction of benzene and chlorine gas, so I will actually write for you, yeah, again, so that we can really understand this concept better. So you see the first thing, yeah, so you have, let's say, for example, you are going to react with benzene and chlorine gas. So chlorine gas, okay, so you have AlCl3 as the halogen carrier or the catalyst, okay, they are going to be approached by Cl2, okay, and AlCl3 is going to polarize the Cl2, so the electrons, okay, will move towards here, delta negative, delta positive. Okay, the delta negative, okay, the delta negative will be attracted over here towards here. AlCl3, you will get AlCl4 minus. That's why they are called halogen carriers now. Yeah, so plus, okay, Cl plus. So this is going to be your electrophile. So what will happen to this electrophile? Simple. Okay, you have the benzene, okay, and then the electrophile will come over here. Normally we say electrophile will attack the benzene. So don't go and actually put the curly arrow like this. This is wrong, yeah? So you need to actually put the curly arrow like this, okay? So movement of electron. Okay, so what will happen, okay, is going to be you are going to have 2 electrons from the ring, okay, will be forming a new bond with the Cl. So the previous bond, okay, with the hydrogen will be shown here. So what happens, okay, the 2 electrons have to actually come back, yeah. They the positive charge, the benzene ring is not stable, yeah, they want it to be stable. So they bring the electron, the 2 electrons back into the benzene ring. So what will happen is going to be you are going to have, okay, a chlorobenzene, okay, and the H plus, okay, will actually be given. And do remember just now, okay, we have this halogen carrier forming this, okay. So what will happen, you are going to give you AlCl3 back and then HCl. Okay, this is going to be the mechanism of the reaction. So the only one thing that I want you to remember over here is, okay, you can still, yeah, use your textbook and so on, okay, but update it with the current syllabus, okay, which is going to be, they didn't mention about FeBr3 and FeCl3. So let's actually use the AlCl3 and AlBr3, yeah, so that is going to be the update, yeah, the update. Now, the other reactions, yeah, so halogen electrophilic substitution or halogenation, yeah, same only, yeah. But if you now you have this methyl benzene, yeah. Now when methyl benzene or other alkyl arenes are halogenated, yeah, because methyl, okay, they are known as, okay, electron donating group. Yeah, so if it is electron donating group, they are going to activate position 2, 4, 6 normally. Yeah, they will activate position 2, 4, 6, but in this case they are going to substitute at position 2 and 4. You can see a mixture. Yeah, you are going to have a mixture of compound. Okay, unlike like just now, there's only one Cl over here being formed. Yeah, but now, okay, when you have this methyl benzene, yeah, you are going to actually activate position 2. This is position 1. And you can activate position number 4. Yeah, so the Cl comes at position 2 and position number 4. Okay, some students will be asking why it didn't go to position number 6. Yeah, if it goes to position number 6, the Cl will come over here, which is the same as position number 2. Yeah, they are the same. Yeah, they are the same. So you are going to get a mixture. Yeah, you're going to get a mixture. Okay, but okay, you have to remember, okay, this happens for methyl benzene. Yeah, so these positions are activated by any electron donating group. So the first electron donating group that we learn is going to be the alkyl. Okay, the alkyl benzene. Yeah, so the alkyl or methyl benzene, they are going to be the first one. But there are other compounds which are going to be electron donating. Later we can also see this. Yeah, so phenol, okay, and phenylamine. But do remember, for this chapter, we will focus on methyl benzene and benzene only. Yeah, so we get a mixture of compounds. But okay, but if you have excess, yeah, if you have excess Cl2, you are going to get something else also. So if it is excess, I'll show you here. Okay, if you have a methyl benzene, okay, and you have excess of Cl2, okay, excess. So what will happen? You are going to get, okay, now you have more than one substitution in the mixture. Like for example, CH3 here. Okay, they will substitute the Cl. They are going to substitute at position number 2. Okay, and position number 4. Okay, remember it's 2, 4, 6 activating. And then you are going to have, okay, methyl benzene here being substituted at position number 2 and position number 6. Okay, position number 2 and 6. And we have another one where you can actually substitute at 2, 4, 6. Okay, so if I put the Cl, okay, I am going to put the Cl here, Cl here, Cl here. Okay, of course, if you want to balance, okay, you have HCl, okay, this is 7, okay, this is 7, okay, so this one is going to be 3. Yeah, balancing is not so important for now. Yeah, so what I want you to know is going to give you a mixture of products. Yeah, so that's why, okay, if excess, you're going to get more mixture of product. Okay, so this mixture of product is very, very important. Yeah, so please take note of that. Yeah, so the next part, okay, is going to be, okay, the bond strength. Okay, so currently the screen is frozen. Okay, let me share the screen again. Hold on. Yeah. Okay. So I hope you can see again. Yeah. So you see the next part, okay, because we are forming the chlorobenzene, yeah, we are forming bromobenzene and so on. Okay, it is important to differentiate, yeah, the bond, okay, between, let's say, for example, the strength of the bond, okay, between, let's say, for example, if you have bromobenzene and I have, let's say, for example, something like this only, yeah. So if you have this, okay, they found out that, okay, the bond length, okay, or the bond strength, okay, of this, okay, the Br and the C in benzene, they are much more stronger. Yeah, why it is much more stronger? Okay, this is going to be explained by the lone pair of electron in the halogen. Okay, they are going to actually overlap slightly, okay, with the benzene ring. Yeah, they overlap slightly with the benzene ring. And what happens in that process, they whenever there is overlap, okay, there is going to create a partial double bond character. So similar, like for example, last time I told you, yeah, if you are actually in taekwondo or something, if you have a plywood, yeah, and then you stack two short plywood together, and you ask to break the plywood, Okay, if you actually try to break over here, yeah, the plywood will be broken. Okay, but if you try to break the plywood over here, most probably only your hands might be broken. Okay, so therefore, yeah, so it's telling you that the shorter bond, yeah, stacked together, okay, it's going to be difficult to be broken. Yeah, difficult to be broken. You require more bond energy. Okay, therefore, okay, you require more bond energy to break this bond. Okay, so that explains, yeah, so they are stronger. Why? Okay, the reason is one of the lone pair, okay, they overlap slightly with the pi bonding system. Okay, so they give you a partial double bond character. So, but do not get mistaken, partial double bond character is not going to actually tell, oh, they will do the they will do the electrophilic addition reaction. No, the partial double bond character is more towards the strength, yeah, the strength or the bond length, okay, of the carbon and Br. So they are going to be a bit stronger. Yeah, they are going to be a bit stronger. Okay. The next is going to be, okay, the free radical substitution. Yeah. Now, earlier we have learned about electrophilic substitution. So this is going to be a different mechanism. Yeah. And this reaction is going to be for methyl benzene. Yeah. And the reaction that the condition is going to be boiling. Now, why boiling? Because free radical substitution, generally we use the sunlight. That's it. Yeah, sunlight or UV light. That's it. The reaction will happen. Okay, but do remember, I told you that benzene or whatever, they do have the benzene ring, which is going to be aromatic stabilization. Generally, yeah, they are difficult a bit, yeah, for reacting. Yeah, they're stable. So therefore, you need to have a slightly, a bit more extreme condition for it to react, yeah, even though it's free radical substitution. So they do react, okay, with chlorine gas. They do react with bromine gas, okay, all under the presence of UV light. Yeah, but do remember, if the Cl, okay, the Cl will not directly come to the benzene ring. Okay, they will not go directly to the benzene ring. Please remember, because in order to go directly to the benzene ring, yeah, you need halogen carriers. Yeah, you need the catalyst. Okay, without that, okay, the Cl cannot go directly over there. So therefore, the reaction is going to be, they will go and react with methyl benzene, alkyl benzene, yeah, something like that. Okay, where if you have like, for example, here methyl benzene, they will actually substitute the hydrogen, maybe one hydrogen they substitute. Okay, and the reaction will be similar with the normal free radical substitution, where one by one, okay, will be substituted. Okay, maybe after that, what will happen? You are going to have, okay, CCl3, okay, one by one. Okay, so that is going to be happening over here, free radical substitution. Okay, so if excess, all three hydrogen atoms in the methyl will be substituted. This is under excess condition. Okay, so do remember this. Yeah, so here, if you go and look at the syllabus, yeah, predict whether halogenation, yeah, halogenation means it's going to be the Br addition or Br addition. When you react with Br, react with Cl, yeah, will occur in the side chain or the aromatic ring. Yeah, direct to aromatic ring, depends on the reaction condition. So now we know, if you go to aromatic ring, you need to have halogen carrier. So the halogen carriers can be AlCl3 or AlBr3. Yeah, but if it is going to be side chain, okay, so one of the example is going to be, if you are using the methyl benzene, then you will have the free radical substitution, and the condition, yeah, the condition must be, the methyl benzene must be boiling. Yeah, must be boiling. So that's why, okay, I put over here, and then with the presence of UV light. Yeah, so this one is what they want you to know. Yeah, and they will test you on this also. Please remember this, because they mention it in your syllabus. Okay, the next part, okay, here, this one you can go through yourself. Okay, not so difficult. The next part is going to be the nitration. yeah, the nitration of benzene. So we have learned electrophilic substitution, yeah, or using halogen, yeah. Nitration is also electrophilic substitution, yeah, nitration. So this is going to be introducing NO2, yeah, into the molecule nitro. So the electrophile, okay, earlier like Br plus, okay, Cl plus. So now the electrophile is going to be NO2 plus, yeah, nitronium ion or nitrile cation. And this is going to be created, okay, using, okay, the what we call as nitrating mixture. Yeah, the nitrating mixture, okay, is going to be a combination, okay, of concentrated nitric acid and concentrated sulfuric acid. So if you look at it, okay, it's going to be, you are going to use these two combination, and you are going to create, yeah, you are going to create, you are going to generate, okay, the NO2 plus, yeah, electrophile. Yeah, it's not showing over here. Okay, let's wait. Yeah, so it's my connection again. Yeah, so NO2 plus electrophile is there. Okay, and this reaction, yeah, is going to be reflux. Okay, condition is going to be reflux. Okay, and then it's going to be done at 55 degrees Celsius according to your textbook. Okay, but if you look at your syllabus, they didn't specify 55. They say that 25 to 60. Yeah, 25 to 60. So that is going to be something that you need to take note. Okay, the temperature that is suggested in your syllabus, okay, is going to be 25, okay, to 60 degrees Celsius. Okay. Let me check whether you can still hear me. Yeah, Erlene, can you still hear me?
Yes, sir, but
Yeah.
quite choppy.
Yeah, it's quite choppy. Okay, but I hope you can still read the notes over there. So basically, it's going to be, according to your syllabus, it's 25 degrees Celsius, okay, to 60 degrees Celsius. Okay, and this one in your textbook, they say 55 degrees Celsius, and nothing wrong. Even I remember 55 degrees Celsius also. Yeah, so this one, okay, you can see the mechanism of the reaction. If you just put it like normal, okay, if you just want to write it down like this, okay, when they react with HNO3, yeah, the NO2, the H from here is going to be substituted by NO2, yeah, so H comes out, okay, H came out, okay, NO2 went in, so there is one oxygen and H left over here. So if you have O and H left over, when you join all of them together, you will get water, yeah, so that's why they put it as water. Okay, but okay, if you want to actually put and show the mechanism of the reaction, this one I'll show you now. Okay, if you want to show it as a mechanism of the reaction, the best way, okay, is to write it this way. Yeah, so I'll just write down first, okay, in the nitrating mixture H2SO4, okay, you mix with HNO3. Okay, what will you get? Okay, if you memorize, it's easier because it's 2. Yeah, you need 2. You are going to generate NO2 plus, okay, and then you will get 2HSO4 minus, and you will get hydroxonium ion. Yeah, this is the first thing that you need to know to write. Okay, so this is going to give you the electrophile. Yeah, this electrophile, similar, they are going to approach, okay, the benzene, okay, not methyl benzene yet, yeah, so it's benzene, okay, they are going to approach, okay, the benzene, and we know that, okay, there is going to be electron rich space over there. Is going to be the benzene ring, so the electron will move towards NO2, not actually the other way around. Okay, but when we say electrophile will be attacking the benzene ring, yeah, but when you show the curly arrow, it's going to be different. So what happened, the 2 electrons from the benzene ring, yeah, they are going to form a new bond, yeah, with this NO2, and then the previous bond, it will stay, H, okay, but now this is not complete, and then a positive charge will be there. So this U, yeah, they have 4 electrons now, not 6 anymore. Okay, they have 4 electrons, and that positive charge is shared across 5 carbon atoms. Yeah, 1, 2, 3, 4, 5. Okay, that's why they put it as U. And then, okay, what will happen? This is not going to be stable. So they need the 2 electron, that went over there. So they need it. Okay, but they cannot actually take it back because it's just formed. So they take it from here, the hydrogen. They bring it in. Yeah, when they bring it in, okay, what will happen? Okay, you are going to get heterolytic fission. Yeah, so you are going to get the NO2. Okay, and then this H is going to become H plus. Yeah, no electron at all. So that is the time that H plus will be there. Okay, you can show it as plus H plus. Okay, but sometimes you can actually join them also here, where they are going to react and give you H2SO4. Yeah, so it doesn't matter. Yeah, as long you show it's H plus, it's okay. You can see in your textbook also they have shown H plus. Yeah, so this is the stage. Yeah, so the explanation over here I already explained. Okay, so I will not go through the mechanism. Yeah, so the mechanism is all here. Yeah, so we will just skip these notes. Okay, but again, towards the end, okay, you see here, okay, they say that there is something what we call as further nitration. So what is further nitration? So the nitration will continue. Yeah, so if the nitration continues, you see, yeah, now I have this NO2 here. Okay, NO2. If I want to have NO2 to come in, yeah, so at what position will they come in? Yeah, so this is what you need to think about. Okay, and do remember nitrobenzene. Yeah, nitrobenzene, NO2 is going to be electron withdrawing group. Okay, so we have learned CH3 is electron donating group. Electron withdrawing group, okay, they are going to activate, okay, position 1, 3, and 5. Currently, they are already position 1 is there. So basically, they say activate position 3 and 5. So what will happen? You are going to have further nitration. You can have, okay, NO2. That NO2 that starts to come in, they will not come in at position number 2. They will come in at position number 3. Yeah, so that is going to be important. And further nitration some more. Now maybe if you have some more of the NO2 start to come in, you are going to have at position number 5. So 1, 2, 3, 4, 5. So this position. So they are going to have something like this. Yeah, so that is what they meant. Yeah, over here they say that, okay, further nitration, they produce 1,3-nitrobenzene. Yeah, or 1,3,5-trinitrobenzene. Yeah, so which is going to be the one that I draw over here. Yeah, so why is this different than methyl benzene? Because, okay, methyl is going to be electron donating group. Okay, and then NO2 is going to be electron withdrawing. They will activate position 3 and 5. That is going to be the different thing over here. Now, we in this table, yeah, they have shown, yeah, which one is electron withdrawing, which one is going to be electron donating. But according to your syllabus, yeah, you need to know. Okay, now based on our notes, yeah, so you have methyl CH3, okay, any alkyl group. I went through this with you. And then I also went through the NO2 with you. Yeah, this is going to be what we went through. Yeah, but what you need to know is also going to be the phenol. Okay, you can see phenol. Okay, any alkyl groups. Okay, so which is going to be any alkyl groups. NO2, you see NO2. Okay, and then another two that you need to know. Another one more is NH2 here, and carboxylic acid and this one. Yeah, so that is going to be carboxylic acid. Okay, and anything to do with this ketone or aldehyde. Yeah, so something like this. So that is going to be something that you need to know, but no need to know the others, like for example CN and so on. No need to know. Yeah, but for now, yeah, if you want to narrow down and focus, yeah, if you want to narrow down and focus, of course, it's going to be you focus at CH3, and this one is going to be NO2. Yeah, so CH3 and NO2, yeah, it's not appearing over there. Okay, CH3, okay, let's actually wait for a while. Yeah, CH3 and NO2, yeah, so this is going to be position 246, yeah, and this is going to be position 135. Okay, so you need to know electron donating, and NO2 is going to be electron withdrawing. Okay, now let's actually move on. Yeah, so this one, okay, is going to be under the alkylation or acylation, and we call it as Friedel-Crafts reaction. Yeah, we have already also done this. Yeah, basically we are going to actually change benzene. Yeah, we are going to substitute or add yeah, CH3 into it, yeah, or C2H5 or any alkyl groups into it. So we can use this Friedel-Crafts reaction, yeah, or if you just want to actually focus on alkyl only, yeah, then we call it alkylation. But if you're talking about acyl, yeah, acyl means this one, C double bond O and then R. Yeah, this is going to be known as acyl. Yeah, so if you want that, then it's going to be acylation. Yeah, so you need to use the catalyst. Yeah, the catalyst is going to be AlCl3. Yeah, but here they didn't explain whether you need to heat and so on. Yeah, so you can see in your syllabus you must heat. Yeah, you must heat, so please actually include that when you explain. Yeah, so you need to heat and then the reaction will happen. So basically it will result, okay, in the introduction of the side chain into the benzene ring. Yeah, so the reaction, yeah, so if you look at this mechanism, okay, this mechanism they show over here is for acylation. Yeah, here they show for acylation, similar reaction. So when you have this let's say for example, sorry, they show over here for alkylation. Yeah, so if you have this Cl, okay, halogenoalkane, yeah, so you want to actually substitute this group into the benzene ring. Yeah, so what you need to do, yeah, you need to show, yeah, the electron will go here, okay, and then, okay, this is delta negative, delta positive, they will go here, they show, yeah, and they will form the AlCl4 minus, and this thing, yeah, this entire thing, yeah, is going to be known as the electrophile. So this electrophile, okay, what they will do, they are going to attack the benzene ring. Yeah, so similar like what we have done. Yeah, so they then you are going to get this. Yeah, and the next step, I think everyone should know. Yeah, they will actually come back. Yeah, they will come back. Okay, and give you this. Okay, but I'll show you. Okay, related to acyl chloride. Yeah, so this one is going to be the normal one, halogenoalkane. Yeah, but let's say I want to actually put, let's say this is going to be benzene, yeah, and I'm going to actually react with acyl chloride, maybe like this. Okay, Cl. I want to put C2H5 over here. Yeah, I want to put. I'm generally going to generate a benzene, okay, with C2H5 over there. Yeah, this is what I want to do. Yeah, so if I want to, I want, okay, I want carbon double bond O C2H5, sorry, and then plus HCl. Yeah, so this is what I want. Yeah, and this is what I want. So what I need to have is going to be, I need to have heat, I need to have AlCl3, very important. Okay, the first thing is going to be, you need to have C2H5, C double bond O, Cl. It will react with this AlCl3. First thing what will happen, the electron will go here, delta negative, delta positive, then it will come over here. Yeah, and you will get AlCl4 minus, and here you are going to get C2H5, C double bond O plus. This is going to be your electrophile. So what happened to the electrophile? Okay, everyone should know. Yeah, so C2H5, okay, C double bond O, okay, plus, okay, let's say I have the benzene over here. Okay, so I am going to draw, okay, this one will go over here. Yeah, so you are going to get, okay, the two electrons will go, okay, so you will have something like this. So the H will be there, okay, and then you'll have C double bond O, C2H5. So the next step, okay, is going to be the electrons. The two electrons will need to come back. Okay, they will bring it over here. So you are going to get, okay, the this one complete. Okay, you have C double bond O, C2H5, and then you will have H plus. Okay, this H plus. Okay, I think you know what to do with this H plus. They will react with this. Okay, they will give you AlCl3 and then HCl. Okay, so all these are the mechanism of the reaction. Yeah, so the one that is missing, yeah, the one that is missing over here. So you can refer, it's the same thing. Yeah, it's the same thing. Okay, so further alkylation can also happen. Yeah, and as the reaction proceeds, but do remember when they say further alkylation, do remember this is going to be 2,4,6 activating. Okay, it's not showing yet. Okay, so do remember alkyl, yeah, or alkyl group. Okay, they are going to be 2,4,6 activating. I was busy talking and suddenly it got disconnected. So do remember, yeah, let me actually share the screen in a while. Okay, but do remember, okay, when you have, okay, alkyl groups, okay, they are going to be 2,4,6 directing. Okay, they are going to be 2,4,6 directing. Okay, just to check, Justin, can you hear me? Ashley, can you hear me? Ashley, can you hear me now?
Yes, sir.
Okay. Sorry for just now, but do remember, yeah, do remember that, okay, if you have the reaction, they say further alkylation can take place, yeah, you need to remember, okay, that, okay, the alkyl groups, okay, that they are going to be 2,4,6 directing, yeah, they are going to be 2,4,6 directing, so you can see here, okay, further reaction, yeah, they can happen, but this is alkyl or methyl, okay, they are electron donating group. So if you have further reaction, yeah, if you have further reaction like this, what do you expect? CH2, or I'll just make it as C2H5, yeah. So if you have C2H5, further reaction will be, you can have at position 2, 4, and 6, okay. So it's going to be, maybe you can have, okay, C2H5 here. Okay, so this one is going to be C2H5, okay, position number 2. And then after that, okay, maybe you can have C2H5 over here, okay. And then after that, maybe you'll have C2H5 over here. That is what they mean. Okay, therefore, you try to relate again, yeah, with this part of your syllabus, okay. Of course, I cannot actually show you all the time, yeah, but try to relate with this part of the syllabus. Hold on, let me see. Okay, relate to, yeah. So always try to relate to this part. Okay, again, coming over there. Yeah, so hold on, let it show. Okay, at the 4, let me, yeah, it's taking too, the time taken to show this is too long. Okay, so Nevan, can you see that? The one that I circle number 4, okay, describe that electrophilic substitution in Arenes, yeah, they refer to different positions, yeah. So this one is very, very important, yeah. So this one I cannot go through all the time, yeah. So basically they are telling that you need to know, yeah, you need to know if you see that further reaction, then you need to apply, yeah, whatever that they mentioned, you need to apply. Okay, that they are going to be 2,4,6 directing. Yeah, so you need to apply yourself. Yeah, so all this we have learned. Okay, but now I'm going to teach you additional stuff, yeah, that we haven't learned. I think this one also we have learned also. Okay, oxidation of the side chain, yeah, of arenes. Now, alkanes normally they are not oxidized, okay, by potassium manganate, yeah. But yeah, if it is going to be alkyl arenes, okay, there is going to be oxidation. So you are going to oxidize to give you carboxylic acid. You do not need to know the mechanism, and I think this one, if you want to memorize also, is okay lah. Okay, but do remember, they are going to give you benzoic acid. I have seen questions where they ask you, okay, let's say for example, I have C2H5 and then I oxidize. Okay, do remember, still you are going to get COOH, not the with the 2 carbon. Yeah. So if you're wondering what happens, okay, to another carbon over there, then they will change into carbon dioxide. Okay, so do remember in your syllabus, whatever methyl benzene or alkyl benzene, you are still going to get benzoic acid. Okay, the benzene with 1 carbon carboxylic acid. Yeah, so that is going to be what is going to happen. Okay, but do remember, okay, this one I think Josh was actually asking about this, which is good question. Okay, they say that, okay, it is oxidized in benzoic acid when you reflux. The condition is reflux must be alkaline, because normally we reflux with acidified alkaline potassium manganate, and after that, you acidify them with dilute sulfuric acid or any dilute acid. Yeah, so it means there is going to be additional step over there for oxidation. So normally we say acidified potassium manganate, yeah, but now you oxidize them with alkaline potassium manganate. Yeah, after that only you go and add, okay, the dilute acid. Yeah, that's the difference over there. Okay, so that is going to be the oxidation of the side chain. Yeah, so don't forget, okay, benzene cannot be oxidized. Yeah, benzene cannot be oxidized. Only methyl benzene or alkyl benzene can be oxidized. Please remember that. Yeah. So the checkpoint you can actually do yourself. Okay, so I'll just move on. Yeah. I think this one we can do. Yeah. Okay, we still have time. So here you see we are going to actually have a benzene. Yeah, and then we are going to mix with this halogenal alkane. Yeah. So if you have halogenal alkane, of course, we are going to actually have this alkylation. Yeah. So you are going to have this benzene, then you add all this, substitute. Yeah, substitute, and then Cl and H, you will have this. So do remember, you see C6H5. Why H5? One of the H will be substituted. Yeah, and the same thing, okay, this is going to be acylation. Yeah, so you are going to have C6H5, okay, and then the rest, okay, and then HCl. Quite simple. Okay, hexyl benzene. Yeah, so you see, yeah, this is going to be alkyl benzene. It's reflux with alkaline potassium manganate and then acidified. Okay, the same experiment is carried out using hexane and the oxidizing agent. Do remember, alkane cannot be oxidized. Alkene can, yeah, alkene can, alkane cannot be oxidized. So if you do this, what is going to be your observation? The purple color will be decolorized. Okay, the purple color will be decolorized. Okay, but there is no reaction with hexane. Simple as that. Okay, now the last one. Okay, the last one that is being added into your syllabus, you will not get it in your textbook. Yeah, please remember this. Yeah, even I was teaching you. Okay, if you remember, I didn't teach you about this. Yeah, this is being added. So this is going to be hydrogenation. Hydrogenation is going to be electrophilic addition. Yeah, they are not going to be electrophilic substitution. Okay, they are focusing on electrophilic addition. And if you can remember what I said about electrophilic addition, benzene, they do not like to go through electrophilic addition, yeah, because of aromatic stability. Why? They need to have harsher condition. This is going to be the harsher condition. Under the harsh condition, okay, which is going to be with heat and high pressure, yeah, they will undergo hydrogenation. So it means they will undergo electrophilic addition. So we are going to actually have, okay, the three hydrogen, yeah, the three hydrogen, okay, basically the six atoms of hydrogen, sorry, there are 6 atoms of hydrogen, okay, will be substituted. So you are going to get each of the carbon, okay, each of the carbon will have 2 hydrogen, yeah. So this is going to create, okay, from benzene you are going to get a cyclohexane, okay. This is going to be cyclohexane. There is no double bond anymore, okay, or basically there is no benzene ring anymore, yeah. So this reaction is going to be using nickel or platinum. This is similar, okay, to the hydrogenation with alkene, yeah. But that hydrogenation with alkene, we actually use nickel and platinum, okay, 140 degrees Celsius, if you can remember, yeah. And this one, okay, because remember I told you you need harsher condition, yeah, we are expecting the heat to be more than 140, yeah. But in your syllabus they didn't mention the heat, they didn't mention the temperature, so it's okay, just heat and high pressure I add to it, because in your syllabus they say they use this catalyst and heat only, yeah, the heat only, but you need to also have high pressure. So I put over the high pressure additional, yeah. So this is going to be what is going to happen, okay. If they ask you the mechanism of the reaction, please remember, okay, this is going to be normally will not happen, but it is going to happen under extreme condition or harsher condition, okay, which is going to be hydrogenation, which is electrophilic addition. Don't get confused with electrophilic substitution, yeah. So do we need to know the mechanism? You can see from the syllabus itself, they do not require you to know the mechanism, yeah. So if you put it as summary over here, yeah, these are the part that under this particular chapter, okay, that we have covered, yeah, up to now, okay. Yeah, it's lagging, yeah, but you can see now, yeah, the summary, okay. I will go through the summary for with you. So you see here, okay, the substitution reaction with Cl2 and Br2, okay, with the presence of this catalyst. So ignore, yeah, ignore, okay, ignore FeBr3 and FeCl3, okay, ignore that, yeah. So that is going to be very important, yeah, when you study, okay, you refer back, yeah, it's laggy towards the end, okay. Please refer back to the syllabus again, yes, even because especially now when it is actually we are talking about, okay, the new syllabus, so you need to also keep on yeah, keep on following that, yeah. So you see here, okay, nitration, yeah, nitration, we have learned about nitration. Okay, do remember concentrated, both of the acid must be concentrated. Okay, so I am using 55 degrees Celsius, is okay. Friedel-Crafts reaction, okay, do remember in your textbook, don't include heat, okay. So we need to include heat, yeah. And complete oxidization of side chain, okay, do remember benzoic acid, okay. And then they didn't say, you know, side chain of what, methyl benzene or what, any alkyl benzene, they will give you benzoic acid, yeah. And okay, do remember this is going to be hot alkaline. Why hot? Okay, this is going to be, I think just now I said reflux, yeah. So hot alkaline, okay, reflux, okay, and then dilute acid, okay, alkaline and dilute acid. I'll just use this one over here. Very, very important. Okay, the difference, okay, with the conventional oxidation, okay, this is going to be, you use hot alkaline, then after that you use the dilute acid, but in my example I use the dilute sulfuric acid, yeah. Now hydrogenation of benzene ring using the catalyst, this is quite common, okay. Additional is you need to include heat, and I also include high pressure, okay. And then you are going to use you are going to get cyclohexane, yeah, cyclohexane. And then I have described the mechanism of electrophilic substitution, yeah. Whenever we form the nitrobenzene, whenever you use bromobenzene, yeah, Even chlorobenzene, I think it's the same situation, but they didn't put it in the syllabus. Yeah, but they can still ask. Yeah. So with regards of the effect of delocalization, so that's why I'm stressing this word. Last time they never used this term. Yeah. So now, since they included that in your syllabus, please try to use this term, aromatic stabilization. Yeah. So if they say why they don't undergo addition reaction easily, because aromatic stabilization. Yeah. So you would say generally they go through substitution instead of addition because of aromatic stabilization. So this is going to be newly included. Now, predict whether halogenation will occur in the side chain, yeah, or in the aromatic ring depends on the situation. So, if you want to have anything to go into the aromatic ring, then it must be with the halogen carrier. Okay, so without the halogen carrier, you are not going to have that. Yeah, but if it is side chain, then especially like for example, free radical substitution. Yeah, so that's going to be the side chain. Yeah, especially I think I introduced a new condition which is going to be boiling if it is methyl benzene. Yeah, so please recall all that. And the last one, describe that electrophilic substitution will go to different part of the ring. And then they say, yeah, the one that is focus is going to be the CH3, the R. Yeah, and then we focus in nitro. Yeah, but do remember they also included all this, yeah, which is going to be something that you need to remember. So you see this one is going to be position 246. This is going to be position 135. Yeah. So this one, all this, okay, is going to be position 246. Yeah. All the others, okay, is going to be position 135, electron withdrawing.
So
Yeah.
what is this? What is aria? Is that like
R
just
is alkyl.
oh, okay.
Okay, so R is going to be CH3, C2H5. Remember one of the example just now, they use hexyl. Yeah, hexyl. So it's not limited. Yeah, it's not limited. Any alkyl groups. Okay, so they are going to be electron donating. Yeah, so alkyl groups. Okay, but generally we use these two terms. Yeah, methyl and ethyl. Okay, but it's not limited to that. So that's why they put it R. Yeah. So every single time when you see the alkyl groups there, yeah, because the number of carbon can be different. You see in one of this example, you see here how many carbons that they use. Yeah. So all this. So this is going to be also going to be 246 directing also. Yeah. So it's not limited. Yeah, it's not limited. Okay. If let's say I ask, okay, whether let's say for example now I have this reaction CH2, CH2, CH3, and they say that okay, this one, yeah, this one will react with Br2, for example. Okay, this one reacts with Br2 with the presence of AlBr3. Yeah, if I put this as an example. So what will happen? The Br have to go there. Yeah, will go directly to the ring, but at what position? Yeah, so you need to determine what position. So because this one is going to be 246 directing, so most probably the Br, okay, will go and enter here. Okay, if you have the Br will go at position number 2. Okay, the Br will go to position number 2. And the Br, okay, if let's say you are using excess, okay, the Br can go to this position also. And the Br later, yeah, 246, yeah. So later they can also go here. So I hope you understand this because I cannot actually show every single example. Yeah. So it depends. You need to identify under certain condition where it will go. Yeah. So in order to understand that, you need to know whether it's 246 or not, 246 directing or not. So you need to actually follow that part of the syllabus, which is going to be was made easier. Okay, with the table. I think, yeah, with this table. Okay, it's actually a bit very laggy in the morning. Yeah, so yeah, you can see the table over there. So anyway, yeah, It's 8:35. I have meeting also. Yeah. That's all from me. Yeah, that's all from me, guys. Okay. So next lesson, yeah, I want you to on Monday. Okay, I want you to focus on the group discussion. Yeah, the worksheet. Yeah. So that's it from me today. Yeah. See you guys. Bye.
Thank you,
Bye,
sir.
sir. Thank you, sir.
Well, sir, thank
Bye, sir.
Yeah. See you.